an adaptive screen space meshing approach for normal integration. Normal integration, that is the process of turning normal maps into 3D surfaces, is renowned for recovering fine and delicate surface details. Increasing the resolution of the normal map improves the accuracy of fine structures. At the same time, smooth, featureless regions will reveal little additional information. However, in both cases, increasing the resolution will yield additional data that needs to be handled during integration. Generally speaking, to resolve structures half the size, both image height and width need to be doubled. This quadratic growth in the number of variables has a significant impact on the runtime of normal integration and makes regular pixel grids an increasingly inefficient geometric representation. To overcome this limitation, we replace the regular pixel grid by an irregular triangle mesh before integration. This triangle mesh is adapted to closely represent the underlying geometry and is controlled by a user-defined error threshold. We can then perform the normal integration on the much sparser triangle mesh, which yields major memory and runtime benefits. For this, we derive a mesh-based formulation of the normal integration problem. To detect regions with fine details, we use curvature. Curvature is closely related to the derivative of the normal map. It describes how a sphere can locally approximate a surface. Loosely speaking, fine details require small spheres and lead to big curvatures. More precisely, curvature can be used to estimate the deviation of our triangle mesh from the underlying smooth surface. We use this estimate to calculate an optimal edge length that keeps the error below a user-provided threshold. To construct our adaptive screen space mesh, we start by covering each foreground pixel with 2 triangles. Then we iteratively refine this mesh. We collapse and split edges to move their lengths closer to the optimal value. We also flip edges that are locally non-Delaunay and move each vertex to a weighted sum of its neighbors to increase mesh regularity. Major challenges arise since all lengths in the error estimate are measured in 3D space, while lengths on the screen appear foreshortened. Before comparing edge lengths to the optimal values, we need to compensate for foreshortening. In the paper, we show how this can be done using the surface normals. The result is an isotropic triangulation. That is a triangulation where every triangle is close to equilateral, but triangle sizes vary locally. The variation of the triangle sizes is exactly adjusted to approximate the underlying surface closely. That is, we get small triangles in areas with high level of detail and big triangles in flat areas. The number of vertices is again determined by the user-defined approximation error. Depending on this user parameter, even at the highest quality setting, we can achieve a 6 to 18% reduction in the number of vertices compared to pixels for the diligent multi-view dataset. This drastic reduction in the number of variables has major downstream effects for our mesh-based integration. To turn this triangle mesh into a 3-dimensional surface, we present a mesh-based formulation of the normal integration problem. We derive and present a triangle mesh discretization of the integration functional. Please refer to the paper for more details. Like pixel-based normal integration, the mesh-based one requires solving a sparse linear system of equations, albeit with a significantly lower number of variables than in the pixel case. In fact, if we increase the resolution of the input normal maps, the number of vertices grows slower than the number of pixels. This lower number of variables also leads to faster convergence of the linear solver and a better runtime complexity with increasing resolutions. As an example, for this 64 megapixel normal map, our method terminates after 5 minutes, while the full resolution integration takes several hours. Visually, the results are comparable. This is due to the fact that our adaptive vertex placement preserves high-frequency features. This becomes even more apparent if we match the number of pixels and vertices. While a lower number of pixels yields blurry surfaces, our adaptive vertex placement can better capture the overall shape of the object and leads to better results both qualitatively and quantitatively. Please visit the project page for code and further information.